Hi guys. All right, let's do group work 3. So the first question is state the limit definition of continuity. This is pretty straightforward. All we need is that the left-handed limit needs to equal to the right-handed limit, needs to equal to the function, and all of these things exist. So in other words, having D and E equals D and E is not good enough. It needs to be like 5 equals 5 equals 5. So, and they all exist. Now I remind you, infinity does not exist. So if you wanted to add and are not infinite, that would be fine. Okay, so the next question was a little bit theoretical. It really made you think about what we learned about when discontinuities happen, where discontinuities might happen. So this says create a piecewise function which has a jump discontinuity at the breakpoint, and that has an infinite discontinuity at another x value. So an infinite discontinuity. Well, we know that infinite discontinuities happen when we plug in and we get a constant over 0 because we know that's going to give me infinity, negative infinity, or does not exist. So I just need to make sure that I have division by 0 without having a 0 in the numerator. Now for my jump discontinuity, this occurs when the left-handed limit does not equal to the right-handed limit. So this is actually pretty straightforward to do. I'm going to create a piecewise function, f of x, and I'm going to separate it 0 just because it's so super easy to plug in 0. And let's say that I have 2x plus 1. So I'll have 2x plus 1 if x is greater than or equal to 0. Notice then that my right-handed limit, the limit as x approaches 0 from the right of f of x, because this is on the right side of 0. We're using that 2x plus 1 to define it, is 2x plus 1, and then I plug in, and remember, when I plug in, I no longer write my limit sign, so this is just equal to 1. So then all I need to have happening here is that on the other side, I need for it to not equal 1. So on the other side, I'm going to have x less than 0. So I need for this to not equal 1, and I need to have division by 0 at some value that's less than 0. So I need for it to not equal 1 when I plug in 0. Need division by 0 at some value less than 0. So a good thing to do here would be like x plus 2. Why? Because then x equals negative 2 causes division by 0. And I just need to make sure that negative 2 doesn't cause 0 on the top. So I'm just going to plug in 1 here. And notice when I put a 1 there, this is 0 from the left. The limit as x approaches 0 from the left of my function is the limit as x approaches 0 from the left of 1 over x plus 2, which is just 1/2, which guess what is not 1? These things are not equal. So I have a jump discontinuity at 0. Actually, let's write that in blue. So I have a jump discontinuity at x equals 0. And we said that we also want an infinite discontinuity. We cause division by 0 there, so x is equal to negative 2. Causes division by 0. The limit as x approaches negative 2 of f of x, well, negative 2 is indeed less than 0, so that's the limit as x approaches negative 2 of 1 over x plus 2, and I get 1 over 0. So I do indeed have an infinite discontinuity at x equals negative 2. And this, therefore, is my final answer, this beautiful function that I have right there. Is it the only possible function? No, there are an infinite number of possible functions that I could have found there. The only thing that had to be true was the left and the right side had to be different, and I had to have division by 0 on the interval that I defined. Okay, so this brings us to our next theoretical question, which is to now create a rational function. So a rational function, a lot of you asked me about this. A rational function is a polynomial over a polynomial. And I want for it to have an infinite discontinuity, which we reminded ourselves occurs when we have c over 0. And then I also want it to have a removable discontinuity. So what we've seen is that removable discontinuities occur when we have 0 over 0 that we can cancel out to become a number. So I just need for both of those things to happen. I need to have some value cause a constant over 0 and some value cause 0 over 0. So I'm going to start with the infinite discontinuity. And I'm just going to look at the function I had up there, 1 over x plus 2. I know that has an infinite discontinuity, but it doesn't have that 0 over 0. So I want 0 over 0 to occur somewhere else. It doesn't matter where, so I'm going to go with 4. I'm going to have x minus 4. Well, right now, in this form, that x minus 4 causes division by 0, but it doesn't cause a 0 up top. So I'm going to put another x minus 4 up top, and now I have a removable discontinuity at x equals 4. So this is my answer, and we can double check that with limits. I can say the limit as x approaches 4 of this thing. Notice I'm able to remove the problem. I can cancel out those x minus 4s, remove the 0 over 0 that was happening, and get the limit as x approaches 4 of 1 over x plus 2, which gives me 1 over 6. So this was indeed 0 over 0 that became a number. But note that f of 4 causes division by 0. Even though I can cancel it out, it still causes that division by 0. So f of 4 does not exist. Here, if I have the limit as x approaches -2, then actually let's write that down before I do this. So that means at x equals 4, I have a removable discontinuity. X equals 4 is a removable discontinuity. And then we created our infinite discontinuity at -2. And when I plug in here, I get -6 over 0 times -6, which gives me a -6 over 0, which we know is going to be infinity or negative infinity or does not exist. That is my infinite discontinuity. So x equals -2 is an infinite discontinuity. So here we really had to rely on what we learned in class about knowing how what we plug in, what we get when we plug in results in the different discontinuities. How a constant over 0 is going to give me an infinite one. How 0 over 0 that turns into a number will give me removable. Note that 0 over 0 that turns into a constant over 0 gives me infinite. And so I'm just going to do this off to the side here so that you guys can see this. 0 over 0 that turns into a constant over 0. So x minus 4 squared. This, while it starts off with 0 over 0 at x equals 4, if I want to do this limit, the limit as x approaches 4 of x minus 4 over x minus 4 squared, when I cancel out my x minus 4s, I end up with 1 over x minus 4. And that 1 over x minus 4 then causes 1 over 0. So that's actually an infinite discontinuity, even though it starts at 0 over 0. So we need for 0 over 0 to cancel to become a number, not to become a constant over 0. Constant over 0 will always represent infinite. Okay, so this was kind of the theoretical part of this group work. Now we're going to do the more concrete question where we have a function and I want to find all of the discontinuities. So remember that our finding of discontinuities comes in 2 steps. The first step is we use the functions that are given to find values not in the domain. And the second step is that we check the breakpoints to see if it is continuous there. And for both of these, I should show clear work. I shouldn't just be like, oh, hey, look, 2 over x plus 2, I've got division by 0 at -2. Okay, I'm just going to write down -2. No, you need to show work. You need to explain to me what you're doing for all of them. So I'm going to start off with my step 1, and I'm going to look at each of my functions individually. So I'll have 2 over x plus 2. Where does division by 0 occur? When x plus 2 equals 0, x is equal to -2. But then I'm checking, is that -2 on the interval? Yes, that means I care about it. So then I say, that means x equals -2, that f of -2 does not exist. It causes division by 0. So hands down, this is a discontinuity. So I'm going to look then at the limit as x approaches -2 of 2 over x plus 2. And when I do that, I plug in and I get 2 over 0, which I know gives me infinity, negative infinity, or does not exist. Because this is not a limit problem, it's a continuity problem, I can therefore conclude that x equals -2 is an infinite discontinuity. Notice, again, I started off by writing the limit sign with my function. That's important. If you don't do that, then you are not doing the correct thing. If you just write down, oh, let me see 2 over 0 on the side right there, therefore infinite discontinuity, that is not right. Because this is telling you to justify your answers using the limit definition of continuity. So we really need to push on that. We really need to say, okay, the limit gives me this constant over 0. The limit is infinite. Therefore, it's an infinite discontinuity. I need to see your limit. So in the second one, we have this function, the square root of x plus 4 minus 2 over x squared plus x. And we actually have 2 things to look at here. So this was our division by 0. And we're going to start off by looking at that, division by 0. So that's when x squared plus x is equal to 0. This is another thing. Show your work. Show me that you are solving this equation and make it clear why you are solving this equation. So I'm going to factor out my greatest common factor because that's the first step of factoring always. And I get x is equal to 0 and x is equal to -1. But are these on the interval? Which is 0 is less than x is less than or equal to 5. And the answer is that neither of them is there. I don't care about either of them because they are not on the interval. -1 is not between 0 and 5. 0 is the endpoint, but notice it doesn't say 0 less than or equal to x. 0 is not actually on this interval. We also have to check for a negative under a square root. So we're saying x plus 4 is less than 0. That's x less than -4. Again, none of those values are between 0 and 5. Okay, so this brings us to our third function. So we had our first function, our second function, and our third function I'm going to do over here, 3x squared minus 14x minus 5 over x squared minus 4x minus 5. And again, I'm checking for division by 0. I don't have anything else to check for here. So x squared minus 4x minus 5 is equal to 0. I need to factor this thing. So I get x minus 5 times x plus 1 is equal to 0, which gives me x equals 5 and x is equal to negative 1. Again, neither of those is greater than 5. This is not x greater than or equal to 5, it is just x greater than 5. So that 5 doesn't count and that negative 1 doesn't count. So 5 greater than 5? No. Negative 1 greater than 5? No. They're not on the interval. We don't care about them. Okay, so that means in step 1, the only value that wasn't in the domain that we got was x is equal to negative 2, which is an infinite discontinuity. So this brings us to our second step, which is to check the breakpoints. Well, it should be noted that 0 is actually also not in the domain of this function, because I can see that there is no equal to 0. So it's not in the domain, but that doesn't change how I'm going to approach this. It's a breakpoint, which means I need to look at the left limit and the right limit. So I'm going to start with the limit as x approaches 0 from the left of my function. My function at 0 from the left is the first one, because those are values that are less than 0. 0 from the right will be my second one. 5 from the left and 5 from the right. 5 from the right have values that are greater than 5. So I'm going to replace this f of x with 2 over x plus 2. And guess what? Every single thing that I am writing here is important and is a thing that you should be writing as well. I need to see not just that you plug in 0 to that thing, but that you recognize that 0 from the left, when you are evaluating that limit, is associated with the function 2 over x plus 2. So now I plug in and I get 2 over 0 plus 2, which equals to 1. Then I'm going to do the limit as x approaches 0 from the right of my function. And we said that on the right side of 0, I'm at that second function, root x plus 4 minus 2, over x squared plus x. And when I plug in here, I actually get root 4, which is 2, minus 2, 0, over 0 squared plus 0, so that's 0 over 0. Which means that I need to actually apply my limit techniques and I need to rationalize here. So I'm going to rationalize and I get the limit as x approaches 0 from the right of x plus 4 minus 4 over x squared plus x times root x plus 4 plus 2. Those 4's cancel out. So this gives me the limit as x approaches 0 from the right of x over, I'm going to refactor that x squared plus x, so that's x times x plus 1 times root x plus 4 plus 2, and I can cancel my x's out. The limit as x approaches 0 from the right of 1 over x plus 1 times the square root of x plus 4 plus 2. And when I plug in 0, I get 1 over 1 times 4, so that gives me a 1/4. Notice that 1 does not equal to 1/4. So that's 0 from the left not equaling to 0 from the right. It doesn't matter that f of 0 does not exist, because the left and right limits are not equal to each other, and therefore x equals 0 is a jump discontinuity. So that was my first breakpoint that I checked. If the left and right limits had been the same, so if I'd gotten 1 for both of them, then the fact that f of 0 does not exist would have mattered, because it would have said this is a discontinuity despite the fact that the left and right limits are equal, and it is a removable discontinuity because the limit exists and the left and right are the same, but the function is different, and that's where removable discontinuities occur. All right, so first we checked our breakpoint 0, and now we're going to check our breakpoint 5. So I'm going to look at the limit as x approaches 5 from the left of my function, which we said is the same as the second function. So now I plug in 5, and I get 5 plus 4 is 9, so that's the square root of 9 minus 2, over 25 plus 5, which gives me 3 minus 2 over 30, which gives me 1 over 30. And then I'm going to do 5 from the right. The limit as x approaches 5 from the right of my function. And we saw that 5 from the right came from the third function. So 3x squared minus 14x minus 5. Over x squared minus 4x minus 5. And when I plug that in, I get 25 times 3, that's 75, minus 5, minus 14 times 5, so that gives me a 0 on the top, and it turns out it gives me a 0 on the bottom as well. So what that means is I'm going to have to factor this thing, and I know that I have a factor of x minus 5, so that gives me the limit as x approaches 5 of x minus 5 over x minus 5. So notice that 0 over 0 that's showing up, the same thing that we had to figure out when we were creating a function that had a removable discontinuity. That gives me x minus 5 over x minus 5. Up here, the other factor will have to be 3x plus 1. And down here, the other factor will have to be x plus 1. Using our technique that we've learned at how to factor when we already know a factor. So then I can cancel out the x minus 5s, and when I plug in 5 again, I get 16 over 6, which is 8 over 3. And guess what? These things are not equal. F of 5 is defined by the middle function. So f of 5 will equal to 1 over 30. Again, that's not really important here because we can see the left and right are not the same. So x equals 5 is a jump discontinuity. And that is my final answer for this question. And this brings us to our last question, which is to find the values of k for which f of x is continuous everywhere. And we're going to follow the same steps that we followed for the last question, which one is to find values that aren't in the domain. And with this type of question, that is rarely a useful step, but in this particular version, it actually is useful. And then we're going to figure out what's happening at the breakpoint. So for my first step, division by 0, that second function is not important. There's no possible division by 0. There is no division. In the first one, I have k plus x. So x is equal to negative k. And what this tells me is there is a discontinuity at x is equal to negative k if negative k is on that interval. Discontinuity at x equals negative k if negative k is greater than or equal to 1. And this is important because these problems also have a third step where we go back and check that. Must go back and check. Okay, so this brings us to our second step. And our second step is to see what's happening at the breakpoint at 1. So my breakpoint here is 1. And I want for it to be continuous there. So I need for my left limit to equal to my right limit. So this is 1 from the right, bigger than 1, and 1 from the left. So I have the limit as x approaches 1 from the right of my function. Again, it's important to write your limits. You can't just plug in. We are actually evaluating limits here. I need to see that you understand what you're doing when it comes to continuity. You're not just plugging in 1, you're evaluating a limit. So 1 from the right is my first function. And this tells me that x gets replaced with 1. So I have negative 11k squared plus 2 over k plus 1. And then the limit as x approaches 1 from the left. That's my second function, 4k x squared plus 18x minus 16k. Again, I plug in 1 and I get 4k plus 18 minus 16k, which gives me 18 minus 12k. And then f of 1, note that f of 1 is defined to be the thing on the right. So f of 1 is equal to negative 11 k squared plus 2 over k plus 1. So f of 1 and the limit from the right are the same thing. I don't really have to think about them separately. I just need to set these things equal now. So I'm going to set equal. So let's set them equal and solve. So I have a negative 11 k squared plus 2 over k plus 1 is equal to 18 minus 12k. And I'm going to start by multiplying that k plus 1 over. So I'll end up with negative 11 k squared plus 2 is equal to 18k minus 12k squared plus 18 minus 12k. Now, I want everything on one side with 0 on the other so that I can then factor to solve this thing. So I'm going to move everything over here to the left side. So I have negative 11k squared plus 12k squared. That gives me a k squared. Then I have 18 minus 12k. So that's 6k, which I'm moving to the other side. So that's minus 6k. So here I combined these. That gives me a plus 6k. So then I'm subtracting that plus 6k. So we'll just write 6k here. And then I'm doing minus 18. So I have that minus 18 plus 2. That gives me minus 16 is equal to 0. And then I want to factor this. So I have k minus 8 times k plus 2 is equal to 0. So those two numbers that multiply to give me negative 16 and add to give me a negative 6. So this gives me k equals 8 and k equals negative 2. And what this tells me is that f of x is continuous at x equals 1 if k is these values. K equals 1 if, sorry, not k equals 1, x equals 1, my bad. At x equals 1 if k is equal to 8 or k is equal to negative 2. But that does not mean that it is continuous everywhere. We had this first step that told us that I have this other discontinuity that involves k. So I must go back and check. So my third step here, I'm checking, do either of these cause a discontinuity? Do either of these cause a discontinuity? And honestly, a lot of people get really confused about this step, so we're going to do our best to understand it. We said there is a discontinuity at x equals negative k if negative k is greater than 1. So let's write that here. There's a discontinuity at x equals negative k if negative k is greater than or equal to 1. That is what we found in our first step. So when I have k equals 8, then I'm looking at x is equal to negative k is equal to negative 8. Negative 8, is that greater than or equal to 1? No. So there's no problem here. It doesn't cause a discontinuity. So we're good. We're going to keep k equals 8. Then we're going to look at k equals to negative 2. So this was our other k value that we got. And so x equals negative k would give me a positive 2. Is 2 greater than or equal to 1? Yes. So k equals -2 causes a discontinuity at x equals 2. So we don't keep it. So the only thing we had to check is -k greater than or equal to 1? In the case of k equals -2, the answer was yes. We don't keep it. In the case of k equals 8, the answer was no, so we keep it. So we can conclude then that f of x is continuous everywhere only at x equals, I'm sorry, not x, at k is equal to 8. And that is my final answer. Voila. All right. Bye, guys.